Dear students, in this lecture we are going to discuss zero power factor characteristic of an alternator followed by Potier triangle. This is zero power factor characteristic of an alternator, which shows variation of terminal voltage V with field current by running the alternator at synchronous speed and maintaining the armature current at its rated value. I am going to explain it in detail. So, how this plot is obtained, that is variation of terminal voltage against field current. First run the alternator at synchronous speed, then connect a purely inductive load as far as possible to get the zero power factor condition, and adjust the field current to get rated armature current. Repeating again, while running the synchronous machine alternator at synchronous speed, load is purely inductive connected to the armature terminals. Then you have to adjust the field current. You have to vary the field current till you get the rated armature current. So, corresponding to that you will get some point, let us say somewhere. Now, change the load which is purely inductive in steps, small steps. So, once load will be changed, armature current will be changed. So, to bring the armature current again at its rated value, you need to adjust the field current again. So, let us say you are getting some other point, because V will be varied. So, you will get another point against some another value of field current, and repeat this step, that is vary the load in small steps and adjust the field current to get rated armature current, and note down that particular reading. So, you will get several readings, and corresponding to those readings you will get one plot like this. Before going in detail, recall the phasor diagram of an alternator. You are aware of all these phasors, EF, ER. This is terminal voltage V, this one, this is V. So, for this condition, when purely inductive load is connected, we know that armature current IA will lag terminal voltage V by 90 degree. So, this is V phasor, then IA will be this. Now, add this drop IARA. So, obviously IARA drop will be in phase with IA. So, this is IARA. And then add this drop IAXL, JIAXL. So, this will be perpendicular to this, and this phasor V plus IARA plus JIAXL will give you ER, this resultant air gap EMF. ER will be V plus IARA plus JIAXL, fine. If we will add further JIAXAR, if IA is this, then JIA will be this, and IAXAR will give the magnitude of EAR, armature reaction drop, this, and finally the resultant of this will be EF, that is this phase. EF is no load EMF. No load means load is not connected, that is load current is 0. Once load current will be 0, IAXL will be 0, IAXAR will be 0, IARA will be 0. In that case, this terminal voltage will be same as that of the EF, hence EF is also known as no load EMF. We discussed in previous lecture while calculating voltage regulation. Now, what happens to excitation? if you want to plot IF, then you know that IF will be in time phase with phi f, field field flux, right? IF will be proportional to phi f, and field MMF FF is proportional to IF. We know that MMF is Ni, number of turns into for any coil. If you want to get MMF, then you need to get the number of turns and the current flowing through that, right? Ni. That is, if IF is 0, FF will be 0. If IF is 0, phi f will be 0, because phi f is being produced by IF. So we can write anyway, whether this way or phi f is proportional to IF. Fine. Phi f is cause and EF is effect. We know that EF is produced as per Faraday's law of electromagnetic induction minus n d phi by dt, right? You know it very well. So E lags phi f by 90 degree. This is cause is leading and effect is lagging, right? So phi leads EF by 90 degree. A phi f is in same phase, time phase of IF, and IF is nothing but proportional to FF. So we can say that field MMF will lead, this is field MMF, red color. This red color is EF and this red color is FF. So this will lead EF by 90 degree. Similarly, this FR, air gap MMF, leads ER, air gap EMF by 90 degree. We know that this resultant air gap, we have two types of MMFs in air gap. One is main field MMF, this, and another one is armature reaction MMF. We have already discussed in the lecture of armature reaction. So the resultant of two MMFs available in the air gap, both the MMFs are rotating at synchronous speed. One is main field MMF FF discussed just now, and another one is armature reaction MMF, and the resultant of two will give you the resultant MMF in the air gap represented by FR. So we can say that the ER, resultant EMF, resultant of two EMFs EF and EAR is resultant air gap EMF, that is result of, that is effect of this cause, which is resultant MMF in the air gap. This ER is nothing but minus J times IA XAR. That's why this vector is shown its head like this. This is J IA XAR, but EAR is negative of that's why shown here. And we know that this is effect of this cause FAR. First armature reaction MMF comes into picture, then corresponding armature reaction drops comes into the picture. So we know that field flux leads the EMF induced due to this changing flux as per Faraday's law of electromagnetic induction. So this lags the corresponding MMF, that is FAR. So we may see that if this is FAR, then lagging means 90 degree. Behind this we have taken the direction of rotation, our convention, okay, like this, anti-clockwise direction. This is our default convention, that phasors are rotating in anti-clockwise direction. So if this is IA, then 90 degree lagging with IA will be 90 degree before this, that is this direction. Fine. And we know that FAR is because of armature current, so it will be in time phase with this. If IA is 0, armature reaction MMF is 0, IA is maximum, this is maximum. We are discussing on per phase basis, so don't get confused. Now if we are going to ignore RA, that is if RA is ignored, then this drop will be 0. Then the same phasor diagram can be shown like this. See, this is V phasor, V. This is IA lagging V by 90 degree because we have connected a purely inductive load, 0 power factor load, to our alternator. Now IA RA drop has been ignored, RA has been ignored. It means now JIXL will be in same phase with this, no drop. We are shifting this line to this because we have ignored this, right, horizontal drop along IA. So this will be JIAXL and this will be JIAXAR. With this assumption that RA has been ignored, we may observe that all the three phasors EF, ER and V are lying along a same line. Means these three phasors will be in same phase with this assumption. Fine. Now, if we will further assume that this open circuit characteristic, we are aware of that open circuit characteristic is plot between terminal voltage and field current, and field current and field MMF both are proportional, right? FF is proportional to IF. So instead of taking IF on horizontal line, if we will take MMF, no problem. So open circuit characteristic taking terminal voltage one side against field MMF or field current, we will get the nature of OCC like this. So we are going to have one more assumption that this OCC, open circuit characteristics, gives the exact relation between this ER, magnitude of ER, against FR, resultant MMF. Here we are taking EMF, here we are taking MMF, right? In OCC also we are taking EMF on vertical axis and field current on horizontal axis, and instead of field current we can take field MMF. So basically we are taking EMF on vertical axis and MMF on horizontal axis. So the nature of OCC will be same, and we are assuming that this OCC gives the exact relation between ER and FR, air gap resultant, means relation between air gap resultant EMF against air gap resultant MMF. That's it. That is given by OCC. Fine. Now, corresponding to a particular excitation IF or field MMF FF, this, the no load EMF is EF. Fine. The same EF. Fine. Now, no load means load is not yet connected. Repeating again, we have not connected any load. Synchronous is running at synchronous speed, synchronous generator is running at synchronous speed. Then for a particular field current IF or corresponding MMF FF, we are getting no load EMF as EF. Good. Now what will happen when we will connect a purely inductive load while maintaining the armature current at its rated value? What we did? We have connected an inductive load to our alternator and adjusted the field current to get rated armature current. Then once load is connected, armature current will start flowing. So all these drops will come into picture. This drop has already been ignored here, RA has been ignored, but these two drops will come into the picture. So discuss one by one. For this drop and this drop, we will see that the net MMF, resultant MMF will be this FR once purely inductive load is connected to the alternator. When load was not connected, field MMF was FF and corresponding no load EMF was EF. As soon as load is connected, the resultant MMF decreases from this to this FR and corresponding terminal voltage reduces to ER. Resultant EMF, we know it very well because this will come into the picture, FAR. This FAR will come into the picture, armature reaction MMF, because once load is connected, armature currents start flowing and corresponding armature reaction will be there and corresponding MMF will exist in the air gap. At no load, in the air gap only one MMF was there, that was field MMF FF. Now two MMFs are there, FF and FAR, main field MMF and armature reaction MMF. So from here we may observe that for this assumption RA, the resultant MMF, this is MMF FR, will be FF minus this. Fine, it demagnetizes the main field MMF, so the resultant will be lesser than the at no load MMF, Fine. Corresponding to this FR, we are getting resultant air gap EMF as ER. Fine. If we will further decrease this ER by IAXL, if we will decrease, then we will get terminal voltage, magnitude of terminal voltage. Fine. So the corresponding triangle corresponding to this ER line and V line, horizontal line, where ER is meeting on OCC and V is meeting on ZPFC, zero power factor characteristic, the same. We are getting one triangle ABC, and this triangle is known as Potier triangle. This triangle is known as Potier triangle. So with the help of this triangle, we will get IAXL, and once divided by IA, then we can get leakage reactance and we can get armature reaction MMF. So two parameters are obtained with the help of Potier triangle. One is XL, leakage reactance, another one is FR, the same. PM will be equal to AB. So the base of this Potier triangle gives armature reaction MMF. If we will maintain armature current at its constant value with this assumption of RA equal to 0, the size of this Potier triangle remains constant, hence can be shifted parallel to itself. We can shift this triangle by keeping this vertex A on ZPFC and C on OCC. We can shift this triangle anywhere because the size will remain constant as long as armature current is maintained at its constant value and RA is ignored. Fine. You may observe this length OA in ZPFC. Here you may mark any point. This corresponds to the excitation, field excitation IF required to overcome the two drops IAXAR and IAXL, that is armature reaction drop and armature reaction leakage drop. Fine. Once field current IF exceeds this OA, only then terminal voltage will start building up. For this condition of armature current being maintained at its rated value and synchronous machine is running at obviously synchronous speed and connected to a purely inductive load. So in next lecture we will discuss the detailed steps of obtaining Potier triangle and then how to get the voltage regulation using Potier triangle method or zero power factor method, right? So don't worry about that, I will discuss, and there you will see as discussed that this length AB corresponds to FAR, armature reaction MMF, that is armature reaction MMF required to overcome the effect of armature reaction drop, and this DB, this length corresponds to the MMF required to overcome the leakage reactance drop. So this is OCC, you are aware of that, and this is air gap line. The linear part is extended to get this line, air gap line, and this side is parallel to AGC, air gap line, and meeting this line. This is line corresponding to terminal voltage, so meeting at D, and this is the point meeting the OCC corresponding to ER line. Fine. So we will proceed the same topic in our next lecture, where we will see the detailed explanation of the method, steps to get the voltage regulation of an alternator by using zero power factor test or Potier triangle. Thank you very much.